Hi, I'm Shani Perera. Today I would like to present you about the rho prime meson photoproduction in ultra-peripheral heavy ion collisions at the ALICE detector. The outline of my presentation is as follows. First, I will talk about the ultra-peripheral collisions, then I will talk about the Large Hadron Collider, then I will move on to the production mechanism of rho prime meson. Finally, I will explain about the results obtained with the star detector. Let me start with the ultra-peripheral collisions. When we direct heavy nuclei like lead at each other at relativistic speeds, there are three possibilities that can occur. Central collision is where the two nuclei collide head-on with each other. Second one is the peripheral collisions where the two nuclei partially overlap with each other. As you all know, strong force is a short-range force. Therefore, in both these collisions, strong force comes into picture. What we are interested in is the ultra-peripheral collisions, that is, two nuclei miss each other by a distance that is greater than the addition of radius of two nuclei. In collisions at large impact parameters, hadronic interactions are not possible. Therefore, it provides an unique opportunity for studying electromagnetic processes. LHC stands for Large Hadron Collider. Large due to its size of 27-kilometer long ring of superconducting magnets, hadron because it accelerates protons or ions which are hadrons, and collider because these particles form two beams traveling in opposite direction at speed of light which collide at 4 points where two rings of machine intersect. Large Hadron Collider is the world's largest and most powerful particle accelerator. All controls for the accelerator, its services, and technical infrastructure are housed under one roof at CERN Control Center, which is located at Geneva, Switzerland. There are two pre-accelerators to accelerate the particles before entering the Large Hadron Collider. Here comes another bunch of beams. Then the beams are going in opposite direction. Isn't that just cool? After they reach the targeted energy, the beams inside the Large Hadron Collider are made to collide at four locations around the accelerator ring, corresponding to the positions of four particle detectors. There are altogether 7 experiments installed at the Large Hadron Collider. A toroidal Large Hadron Collider apparatus, which is called ATLAS, a Large Ion Collider experiment, which is called ALICE, Compact Muon Solenoid experiment, Large Hadron Collider Beauty experiment, Large Hadron Collider Forward experiment, the Total Elastic and Diffractive Cross-Section Measurement experiment, and finally the Monopole and Exotic Detector at Large Hadron Collider. Among those 7 experiments, ALICE, ATLAS, CMS, and LHCb are large experiments installed in 4 huge underground detectors built around the 4 collision points of the Large Hadron Collider beam. I'm doing the experiment with the data obtained at the ALICE detector. ALICE detector focuses on the study of heavy ion collisions at ultra-relativistic energies and is specialized in measuring and analyzing lead-ion collisions. ALICE detector is 26 meters long, 16 meters high, and 16 meters wide. Each beam consists of nearly 3,000 bunches of particles, and each bunch contains as many as 100 billion particles. The purpose of the large detectors installed at the Large Hadron Collider is to identify the secondary particles produced in collisions and to measure their positions in space, their charges, mass, and energy. To do this, detectors have many layers or sub-detectors that each have a particular role in the reconstruction of the collisions. ALICE detector is divided into two parts, the central barrel and the forward muon arm. The central barrel of ALICE detector is composed of various detectors for tracking and particle identification. The main tracking device is the time projection chamber. The TPC is a large cylindrical gas-filled drift detector with two readout planes at its end caps. In addition to particle tracking, it provides particle identification information via the measurement of the specific ionization energy loss. The momentum and the angular resolution provided by the time projection chamber is further enhanced by using the information from the silicon inner tracking system. Silicon inner tracking system surrounds the beam pipe. It is employed for low momentum tracking, particle identification, and primary and secondary vertexing. Outside the time projection chamber, there are two large particle identification detectors, the transition radiation detector and time of flight. For each collision, the physicist's goal is to count, track, and characterize all the different particles that were produced in order to reconstruct the process in full. Just the track of the particles gives much useful information, especially if the detector is placed inside the magnetic field. The charge of particles, for instance, is obvious, since particles with positive electric charge bend one way and those with negative charge bend the opposite way. Also, the momentum of particles can be determined. Very high momentum particles travel in almost straight lines and low momentum particles make tight spirals. In ultra-peripheral collisions, two types of electromagnetic reactions can occur. A photon from one ion can strike the other ion, which is called photonuclear reaction, or a photon from each nucleus can strike in a photon-photon collision. Only photonuclear interactions can produce a vector meson. A vector meson is a spin one particle in which the spins of the quark and antiquark points in the same direction. In the Alice detector, ultra-peripheral lead-lead photonuclear collisions produce excited rho vector meson which decays into 4 pions. I will be measuring 4 pions photonuclear production in ultra-peripheral lead-lead collisions at 5.02 tetra-electron-volt per nucleon energy from the Alice detector. First, I will select the ultra-peripheral collisions. Then I will select for track quality. From the track quality, I will select the events that have 4 pions. From 4 pions, I will reconstruct the mass of the excited rho meson. Excited rho mesons has been observed at star detector for 200 giga-electron-volt per nucleon energy, but it has not been observed at high energies around 5 tetra-electron-volt per nucleon. This plot shows the distribution of ionization energy loss in the TPC. The horizontal axis is momentum in units of giga-electron-volt. Momentum is measured experimentally at the TPC. Vertical axis is energy loss in TPC. As you can see, each particle species has a characteristic curve which are clearly distinct for low momentum values. In other words, the contamination from other particle species are very little at low momentum values. Since I am interested in pion curve, I will be considering momentum less than 0.7 giga-electron-volt. The distribution of 4 pions transverse momenta is shown here. While the horizontal axis is transverse momentum, vertical axis is number of counts per 20 mega-electron-volt. The transverse momentum distribution for 4 pion combination exhibits an enhancement at low momentum events. Therefore, events that have transverse momentum less than 150 mega-electron-volts are selected. This is a result obtained with the star detector at a low energy. This shows the invariant mass distribution of coherently produced 4 pions at 200 giga-electron-volt per nucleon energy. The uncorrelated 4 pions invariant mass spectrum exhibits a broad peak around 1540 mega-electron-volts. The ratio of coherent excited rho production cross-section can be calculated from the yields which are determined from the 4 pions invariant mass distribution. I am planning to reproduce this invariant mass distribution of coherently produced 4 pions at 5.02 tetra-electron-volt energy with the data obtained at Alice detector. As excited rho meson decays into 4 daughter pions, first I will select the events that have 4 pions of total charge 0. Then I will measure the momentum of the track and use the energy loss in time projection chamber curve to ensure that each daughter particle is a pion. Using the mass and momentum of daughters, energy of daughters will be calculated. Then, using the conservation laws of momentum and energy of parent particle will be determined. Finally, mass of the excited raw meson will be calculated. To summarize, ultra-peripheral collisions have purely electromagnetic interactions. The vector mesons are produced at photonuclear interactions. The excited raw vector mesons has already been observed at relativistic heavy ion collider for 200 gigaelectron per nucleon. And I will analyze excited raw vector mesons on data obtained with the Alice detector at 5.02 tetra electron volt per nucleon. These are my references. I would like to thank Dr. Seeger and Dr. Wong. Thank you for listening.